Hi, this is Dr. Goldstein, and I am going to be discussing the formal definition of the derivative. So the definition is that the derivative at a point x equals c of a function f of x is the number f prime of c equals the limit as h goes to 0 of f of c plus h minus f of c divided by h, provided that this limit exists. So we will talk in later videos about what happens when this limit does not exist. But for now, the derivative of this function is this number that is the value of this limit. So the way to understand this definition of where it's coming from is you can think about this as the limit as h goes to 0 of average rates of change of the function f of x on the intervals c plus h. That should be a square bracket. So we can think of it as the average rate of change on these shrinking intervals that go to just the point C. A way to visualize this is as the limit, again, as h goes to 0 of slopes of secant lines through the points c f of c and c plus h f of c plus h. So this is a fancy way of saying you take a point where you want it on your function at c, and you take a point a little ways away at c plus h, and you bring that second point closer and closer and closer, and you look at the line between those 2 points, and it's going to get closer and closer and closer to this tangent line, and you take the slope of that tangent line. So I will show you a picture of that later, but for the moment, let's just look at both of these formulaically. So if we look at the average rates of change of our function on these closed intervals, what we're looking at for one average rate of change is f of c plus h minus f of c, that's the change in f, divided by c plus h minus c, that's the change in our x values. And so on the bottom here, you can see that you can cancel these c's, and you end up with f of c plus h minus f of c divided by h. And we're taking this limit as h goes to 0, and that is what leads us to the definition above. So likewise, if we're looking at slopes of secant lines, we have the change in our y value, which is given as f of c plus h minus f of c. Hopefully that looks familiar. That's one y value minus another y value, divided by the change in x, which that's going to be, again, one x value minus another x value. And hopefully that looks really similar to what was written above. And again, in the denominator, those c's cancel, and you are just left with f of c plus h minus f of c divided by h. And again, the idea is we take that second point and we drag it in, so we are taking the limit as h goes to 0. So computationally, these ideas are identical to each other, but it's a very, very different way of thinking about how to measure the derivative of a function. And remember, the derivative is always a measure of how much the function changes at equals c. We're asking how steep is this function, how much are the y values of this function changing as the x values change. So here's two different ways of thinking about it, and they both lead to this same definition. So let's see an example of applying this definition. So we are going to look at f of x equals x squared, and our point is going to be c equals 3. So again, what we're computing is f prime of 3, and this is accomplished as the limit as h goes to 0, f of c plus h, so that's 3 plus h in this case, minus f of 3 divided by h. And so let's take a moment to evaluate what is f of 3. Well, f of 3 is just going to be 3 squared, which is 9. And let's take another moment to evaluate what is f of 3 plus h. Well, that is going to be 3 plus h squared, which is 3 plus h times 3 plus h. And so that is 9 plus 6h plus h squared. So if we take those two quantities and we plug it back into our limit definition, we are taking the limit as h goes to 0 of 9 plus 6h plus h squared minus 9 divided by h. And notice if you just plug in h equals 0, you're going to get 0 over 0. So this limit is of the form 0 over 0. But we can simplify very easily. Those 9's cancel out. And so we have the limit as h goes to 0, 6h plus h squared over h. And now we can factor an h out. We have this h, and so we're left with 6 plus h on the inside. Now our h's cancel, and so we're taking the limit as h goes to 0 of 6 plus h, and so that is just 6. And so this is the value, f prime of 3. And again, this answers the question of how much is f of x equals x squared changing at x equals 3. And our answer is 6. And the numbers don't really mean anything unless we give them some context. So how much is 6? Well, it's positive is one thing we know. So we know that our function is increasing there. We know that it's going up. But yeah, how much is 6 exactly? So let's look at a picture. Okay, so here is my graph f of x equals x squared, and I have drawn the point 3, and so here is my graph is not very to scale, but here is the point f of 3 on the graph, and the idea is if you take a point out here at some 3 plus some relatively big h, you can look at the line that goes through those 2 points, and that is the secant line through those 2 points. And you can say, what is the slope of this line? And you can take that point and you can drag it a little bit closer. So what if we look at this point? And so this is 3 plus h for a smaller h. And you can again look at the line that goes through those 2 points, and you can ask, what is its slope? And we could do this again. We could take a point even closer right here at this 3 plus h, and we can look at the line that goes through those 2 points. And the idea is that as h goes to 0, we are just going to have this one point here, and we can look at what do these secant lines get closer and closer and closer to. So this is the limit of the secant lines, and that gives us the tangent line to the function f of x equals x squared at this point. And the value 6 that we found on the previous slide, this was f prime of 3, this is the slope of that tangent line. And what it represents is how much that function is changing at that point. So the idea is, again, as you take this point at 3 plus h and you make h smaller and smaller and smaller, your secant lines are going to get closer and closer and closer to this tangent line. And so we look at the slopes of those lines and we take the limit of their slopes as our derivative, which is the slope of the tangent line. And this represents how much our function is changing at that